Thank you. Well, hopefully the microphones are working and things like that. So today is more a story than a seminar. It's a story built on many years of being involved in the industry, many disappointments as well as happiness and achievements. This comes out from working with that GCC we mentioned, with the UCT team, back to our Mintech days, with the JK team, with the SMI. It's like an unknown collaboration with me. It's the ideas that have gathered in my mind over a long time. This is not a solo effort. This is not Malcolm's creation. It's me expressing it. And I hope I do it justice. And I hope to bring people on the journey that we're going to express, I'll express today. So I also couldn't do it without the extremely capable input of Jane and my long-term partner in crime, Grant, who's managed to make it here, thank you, who put a huge amount of work into changing my idea into something that I can make into a real story. And I think there was 3 months' work to create it into that, and there's actually real simulations behind this, not just the story. So integrated process prediction, I guess, should be the dream of what we want. We want to link the rock to the final process, the rock to the final products, most of which we call waste. And what I'm trying to dig into is the technology to do that. What do we seem to be missing as an industry that we require in that? But let's drop to the motivation. Why would we go to the effort of doing this? And hopefully it'll move on from the white screen shortly. So I employed the skills of a hitherto unknown but soon to be famous cartoonist in Australia to do this for me. And we might have an ore body with some bunch of ore in it, some deleterious elements. We dig a road through the process. We then make sure we build a huge, big plant that's going to be there for 100 years. We put a whole bunch of yellow trucks to transport the material out the pit. And then we say, well, where is it, as our second point? Oh, it happens to be in mountains with a stream. Well, that valley is a very useful place to put a nice big tailings dam. We'll divert a bit of the water around it. And then we've got our basic setup here, but we need to get stuff in and out, so we need a whacking back, great big road through the environment with a bunch of trucks coming and going, lots of consumables, equipment before and consumables during. So we need a great big road there. We kind of plow our way through the local societies who are not necessarily happy with the dust and the noise and the incursion on the environment. And then we later on say, well, we've got some satellite pits. We might see if we can do something with them later. But let's get to the big one because it's all about economy of scale. And we need a great big power station to power it. We might have lines up there. We might build one. And then we look at over the years, like how many years will it take before we earn anything out of it? It takes a long time to get it up and running, a long NPV payback. We get income from it, and then it tails off, whatever, 15 years, whatever, that our mine is finished. So then we think about an alternate. So I want to consider, what if I wanted to put something completely different on the table? How would we decide whether it's viable? How would I convince a mining company to sink $1 billion into it? So I have precisely the same pit. But I now think about my satellite pits at the beginning, not at the end. I'm thinking about them as a core part of my asset. And I think about where I am first, not second. What's my environment? What's in place around my ore body? And then I start thinking about, can I make these little satellite pits my early ore bodies instead of my end-of-life ore bodies? And could they be something the community builds, processes? They're the early starters. They can be small, viable for the community. So in fact, I can use those to get the community involved and trained for my big process that's going to come later. I'm now going to put in processes that are much smaller. So I have a smaller road and I can send it on a longer route, alternate route. I can avoid the communities, rather put access to people on the road rather than plowing through them. So I can think about my process completely differently if I'm transporting maybe 20% of the stuff to and from site. Then I think about my years that I'm going to go through. These are the various years in the boxes of my processing. And I might actually move my mineral processing plant around the pit. There's no big plant there anymore. It might be a small modular movable one. And actually it moves every 7 years, 5 years to a different spot to cut down the transport, to make it accessible to the pit. Because these are much smaller, I'm now maybe using some green energy, as it might be called. So renewables with a small generating plant, not a big electricity generating plant, but just a small generator. Energy is less than 20% of standard, which is viable. My ramp-up's much sooner. There's a small ramp-up really early on, which is community mining. Then it ramps up a bit more. Then I have the full mine. And when that's not viable for my great big company, I might then hand over to them to continue mining for years afterwards. So is it a 50-year life for the community? A very slow wind down. Been in Turkey at a conference there, and there was a lot of really good presentations around this interaction of a mine with an environment, especially from South Africa, including Jeremy Mann. And so we think about trying to get the image up again. So we think about where our mine fits in, not just that we can make money out of it, but how do we fit it in the community and link from business as usual? How do we connect it to the alternate scenario? What's the key to unlock that alternate scenario? Because if I present that, a mining company is going to say, it sounds very nice, Malcolm, but we have no idea whether we're going to make money out of it. How do we link these new processes you're talking about? How do you predict what they're going to do? And that's when we come to the technology. So what's the technology to move towards that aspiration? So where does it all start from? Well, it starts with core knowledge, I guess is a good phrase to use. You need to know what's in the ground. It's all about the rock. You need to understand what the rock is. And an inspiration moment, maybe 4 or 5 years ago, was actually the properties of the rock don't change. So the rock, you just make it smaller into smaller bits. So in fact, you've got the properties you need in situ. You don't need to reinvent your tests all the way down the process line. We have different tests all the way down the process line at the moment that are equipment specific, which intrinsically means I can't use them to predict the performance of a novel piece of equipment. You're flawed before you start. And this is a barrier to implementing a change in process, a change in technology. So if I can take those and look at their primary properties, I'm now in a position, potentially, to predict all the way down the process chain. So that's what my basis is, just start with the rock. And when I understand the rock, these scenarios, which I'll come back to at the end of the presentation, can I predict what the outcome will be, not just in recovery, but in the total process and total impact and varying the process. So I want to link the rock property to the process to the risks. And there's an excellent set of work done around the risks from Rick's group, and that's what we used as the link. Let's understand how our process links to technology, our rock links to technology, and links to the risks that are preventing the mines being utilized, our resources being utilized. So we want to start by exploring what's out there, understanding what's in the rock, using smart geologists like Alice to describe and quantify what's in the rock. Then we want to look at plant design. Do we have a simple plant design? Do we end up with planning plant expansions when we start the plant, rather than after thinking, how am I going to fit 3 more mills in here and another crusher? And they get quite complex, the expansions. And I'm seeing more and more really complex, difficult to operate expansions. Can we plan those in the beginning? And then we can think about our blast design, which has significant impact on your downstream processing. It interacts with it. It's not just a feed forward, and how we control our blast outputs. And then do we just dig it up and drive it out the pit? Do we do in-pit crush and convey. That's rock dependent, whether we can do that, and blast dependent, the process we use. Can we use ore sorting at a faster rate than a professor with a gloved hand picking up rocks? And do we do better at the handover? It's currently mine handing over to mill at a gyratory crusher with a nice big rock stuck in it. So can we get around those processes? How do those processes affect the entire process? And then we go on to classification and comminution. So the comminution, do we go for the big mills like we are now? They just get slightly longer. We're at 24.5 megawatts now. Do we go for something more novel like an HPGR that's taken 20 years to come in, and Mike, who's here, spent many years studying those. They have their pluses and minuses as well. Can we use them really differently instead of swap a mill or a crusher and put an HPGR in, or something else novel? And classification, which determines whether we've done enough comminution work, the energy intensive process, to hand over something usable for recovery. Screens are great, but they have limited area. Excessive area for limited throughput. Cyclones, fantastic throughput, inefficient. Can we move beyond them? What's the influence if I switch between them or put in a novel classification system? So what if LAD does some great work, we have a completely new classification system? How am I going to predict its influence all the way down the stream? We need to know what it's receiving. We need to know what's in the particles coming to it. And then I want to separate it. And this is where I critically need to know what's in the particles, the distribution, the properties in the particles. Can I go physical separation mode? Is it staged with a physical and then a chemical? Back to my standard large flotation cells, which seem to be getting larger and larger. And what's my influence going to be on water? So can I plan in, before I dig any rock out the ground, what each process will do to water recovery, to water usage? And what will I leave as a legacy? Will I be able to dry stack? Will I try and filter it at more expense than comminution, energy expense, the current filtering processes, which doesn't necessarily seem sensible. Where's my energy going to come from? How am I going to move it to a final product? It's going to produce steel. What's the final product going to be? Moving more towards the life cycle. So that's the product stream. The other stream, which is usually 99% of it, is my waste. What is my waste going to look like? Is it going to be a terrible landscape like this? Is it going to be greened out? Do I have a plan in advance of knowing what the content of those will be, so I can actually plan to change that impact and change how to rehabilitate? Will I end up with a nice green park rather than a pit if it's near an urban area? So I've been around that circle, and what I want to do is relate it to these risks. So the risks that were brought up that are preventing, is it 2/3 of the future world's known copper resources being mined, something around there? And they're not just about grade. So grade is definitely part of it, because if you've got low grade, you can't make money out of it. So that's definitely a driver. Can we address the problem that it's low grade and expensive to process? And your resources, the impact on water, the requirement for energy, big pushback. Sweden's trying to go fossil fuel free by 2030 or something. ITEC mine I was at is looking at how do they change the entire mine to not using any fossil fuel at all, on the assumption that they can receive unlimited amounts of energy over an electrical line. And the tailings, which has really raised its ugly head in our industry, and I was quite shocked to find out how many tailings dam failures there have been. So more than 50 in 10 years. I had no idea. They're too small to hit the news. We just hear the really catastrophic ones. So this is an endemic in the industry. So are we ever going to get a license to put in tailings dams today? And should we get a license to put them in? So how do we address that? Can we look at our rock and decide we can change the process to change that profile? And the variability strikes us as a complexity of processing, or you have to upgrade as you go because your ore is too disseminated. And then permitting can take, 7, 10, 20 years. How do we address the permitting? Are we able to, early in the game, be aligned with what's required in permitting? and which links to the legal side. So what are the community, what are local aspirations, what are the requirements to be in the environment, to put in roads, to dispose material. And then naturally linking with the community, do we have the big no, or do we have a coexisting society like Manoa, a kind of symbiotic relationship there? And these artisanal and small-scale miners, instead of taking their livelihood away, can we make them part of the mining process, an integral part, but not mining like that? How do we address that, keeping their livelihood, but not destroying their lives, as I see there? And of course, acid mine drainage, which we're pretty good as an industry, but something you can never escape from, the problem. And can we go back to biodiversity, not a monoculture, even if we rehabilitate? Do we go back to where we were? Or do we go to something better, which has been raising its head? Well, why go back to what we had if we can actually enhance it? And then the infrastructure. A lot of the new ore bodies are in remote areas, third world countries. Do they have the infrastructure of the power, the roads? It's a big barrier to implementing these huge mine sites. So that takes us around the drivers that we need to maybe influence, that we need to accommodate to be able to utilize our resources. I very much see it as a utilization of resources for society. Otherwise, what's the purpose? And now we're going to look at the technology. And it comes back to what I've called primary rock properties. And it's come out of a geological definition, actually. And if you can understand what is in situ in the rock, it's not about it's a response to a given test somewhere down the process line. What you want to do is carry the primary property and predict responses all the way down the processing line, not measure response at that particular point. Because if you do that, you have no way of escaping your current process. So you want to predict. So can we map into the ore body? Simple geological map here. Maybe Rick would say it's not simple to get there, but it looks simple on the screen. This is some great work that Barry Shieldrum did, which was exploring this. So I was exploring it. It was a porphyry copper. We are continuing the work, as we know, so there's potentially some great stuff to come out of this. But it's, can we look at a primary property, which was strength, force to fracture, or energy to fracture, versus the alteration. This was replaced in plagioclase. And it's got a pretty good linear relationship, and that's about 70% of that ore body. So that's a strength of the particle is a primary property. It is in fact the same strength that Sham would use in his blast design. You're measuring it slightly differently, but actually you can calculate the one from the other. So it's coming back to, well, we actually want to know the strength, don't we? And then we'll figure out how it responds in a SAG mill, ball mill, crusher, blast, etc. Naturally, with structural process and blast, you need to know the structure in the rock, not just the strength of a little one. But this is the primary rock property of the strength here. We can measure it by doing careful measurements like this, and hopefully much faster ones, which has driven me to work on a device that's sitting down in the labs to do this really fast. And you can get a strength distribution, not just an average number, and see how that distribution goes through the process and how that blending of distributions will go through the process. If you understand a strength distribution and can use it, you can deal with blends, which are pretty poor at the moment. When you take that, I've got a strength. I now need to carry it through the process. What I see is particularly weak in our industry is we have a rock strength, we have a floatability, we have a recovery, we have some indicators about tailings, remediation, but we're not actually carrying the heart of the problem with us, which is the mineral association. Mineral processing is all about mineral association, and I do not see a model out there that actually does this. So we do not model the process by the heart of the problem, which is the mineral association in situ, which we then want to separate out so we can recover the valuables. So we need to know what's the association of the valuables in the gang all the way through the process to know where we can capture it. to know how much work we should do on it. So having a model that can understand or carry the information of mineral association underlies us. And fortunately, the very smart Marco Hilden, who happens to be on Bada Hiju mine today, that's why he's not here, him and Mosen, has developed a model that's definitely working, but it's still a fledgling model. But it can take multiple minerals, 3 or 4 minerals, minerals within minerals, and carry them in quite a simple mathematical form. That's fast. So you can simulate anywhere down the process chain in 10 seconds a whole mineral distribution, mineral association. I'm not going to use the word liberation because it's not about liberation. It's the association of what's attached to what, what's associated with what. This is incredibly powerful, and that, to me, is an underpinning area. You know, and Kathy and Lane have been working on how to understand it in a rock as well. That's a really key part, but seeing such a tiny bit of the work we do, yet it totally underpins the entire industry. This, to me, is where we should go. If we have this, what can we do with it? Well, if I take that, the structure, the mineral structure in a block, and I can do 10,000 of these, I can do the variability in the blocks, I can do the variability around the ore body, I can actually simulate them really fast, is that I can then look at how it moves through the process and how the mineral association changes, and how it changes with different processes. So we'll start with a simple one where we've got a sag feed. So here we've got a few minerals, and we've got whether they're liberated all the way up to binaries, tertiary, highly complex, and we've got our non-sulfite gangue, pyrite, etc. So in the feed, they're pretty well associated. That's why we're putting it through the sag mill. We then go the sag products, and quite a lot of them are liberated now, but many are still associated with each other. And then we get down to the cyclone overflow, and we have considerable liberation and some association. This is entirely from Marco's model. Those are predictions from his model as he goes down the process stream. Now, we've applied it to conventional, but that could apply to any new super jumping, wiggling comminution device. It's not locked into a given process. If we take an advanced miner mill with all our measurements and things, can we now look at how that changes the process? It'd be really nice if the predictor stayed on. Unless I pressed the wrong button. Thank you. So I go through the mine to mill process, and I look at what I can do all the way down the process line. So I go to ore sorting. What's the minerals I'm going to have, and how they're going to vary over time? How effective will my sorter be? Will it be unutilized, sometimes heavily overutilized, other times ineffective, highly effective, because we have a variable ore body? Can I predict that all the way through a month, a day, a month, a mine life? And then how effective is it if I have a belt scale one, a particle scale one, which parts of the ore body I should use it on? So we can start looking at that process because we know the mineral association of the particles coming through. So we can look at that well in advance before we do any process design. If I look at the specific energy, my favorite of size-specific energy, along the process, what's the energy required to achieve those targets that I want to look for? Can I map that? Can I see where I'd be relative to the world and the current processes if I use a nice map like this of the energy intensity across the entire industry? Where will I sit? And will I push my material into the recovery regime? So I talk about a recovery regime by size. What's the window I want to be in? That window will move depending on the upstream process, of course, but it's all about the mineral association. So if I'm understanding where the minerals are and the particles coming down, I can understand where my window is going to be for different recovery processes. So each recovery process will have a different window for the same mineral. Am I producing a whole lot of fines, wasting energy, which is our standard practice, with some stuff that's too coarse? So we move the whole distribution finer to try and recover the top shoulder. Can I make it steeper and keep it close in the window, or can I optimize it and move it so that it's all to the right-hand side of the window? Massive difference in energy consumption. and in fines production, and the fines affect water recovery and tailings. So if I change the process to still be in the recovery window, I can change the entire impact on the environment massively, not by 1%, but by 50, 70%. That would be my target. But I still need to recover the minerals, which is not much of a going concern, is it? So now I look at, if I change my classifier, and this is work done here at the JK with Juan Ko and Kim and Grant, I have the mineral and the ore distribution at the end of the classifier and the solid lines, and the dotted lines are where the minerals are. There's a big difference in mineral size distribution versus ore coming out the product for a cyclone, and not that much for a screen because they classify differently. How does that affect your recovery curve? Is it the same? We doubt it. So you actually need to then interact with what it does to your recovery curve. The mineral association is different coming out those two processes. And if you go for a non-mechanical, so this is work Frank did with one of our students on looking at, with the cell frag from mechanical versus cell frag, had quite a different grade recovery curve. And how do we get that into our process? We're not particularly good at that at this stage. But if you understand how that affects the fragmentation of the rock, you can, again, understand what the rock appearance is afterwards. And then you can look at, well, how is it likely to attach to a bubble if you go in flotation? And you can look at, for mechanical or non-mechanical, as I move the particle size finer, so this is a theoretical calculation based on mineral association. As I go finer, for a given mass recovery, say 40%, what's my metal recovery limit? So this is the ideal limit. Doesn't mean I'm going to achieve it. And the sooner I start it, the lower my metal recovery. The later I do it, the higher the metal recovery. So if I start in-pit sorting versus at flotation, have completely different profiles of recovery, but really different impact on process size, energy use, cost. And can I understand that through the process? Can I understand doing this 4 times rather than once? So that's staged upgrade. So I take just a tiny bit out to start with and get a really high metal recovery, and then a bit more and a bit more. Can I understand that process? We're not good at modeling at the moment. But to understand the impact, the value of it, you need to understand what are the minerals that are left, what's the association of minerals left after I've done a first upgrade, and how's that going to vary as the ore body varies. And I spoke about the water a bit earlier on. We know that water is basically associated with the ultrafines, -10, -20 micron. I couldn't find published data on this. I hope it's out there somewhere. But we've got a -74 micron, which is a bit crude. But we know for sure that the finer the product, so the more fines you have, the greater the moisture it retains. It's the surface energy problem. So if we can dramatically reduce the amount of ultrafines we're producing that we don't necessarily need to get our mineral recovery, unless you're in platinum potentially, Neville? So one place you might, for part of your ore body. And generally you don't. You've got a porphyry copper, coarse gold. You don't need the -10 micron at all to recover the material. If we don't produce it, we don't have to filter it and dry it. And there's a huge impact if we change the process on the impact it has downstream. And then can we look around the whole life cycle, like Glenn Corder's doing, Marston's getting involved in the whole life cycle of where we fit in that life cycle and how we affect it. We are having industry coming to us as the end user drives the process, our process. So we've got a product, but what about the rest? If we can look way ahead into the future, know what, dependent on the process route we use, what is our waste? What are our tailings going to be? What is our waste stockpile going to have in it? What will the association be in the waste, not just the product? Because that determines whether you're going to get acid mine drainage. You can even look at size distributions for stability. So that's would be an idea of understanding what the minerals are left in our waste stockpile. And then how that will affect rehabilitation, going through evolving a new environment after we've moved on. So that takes us around the circle technically. So what I'm trying to inspire there is the understanding that technically if I can put my finger on what those processes will do, I can change the outcome of the process. Not a little bit, but dramatically. So if I look at a mine site, and I've got the mine, I'm going to do a designer stage upgrade, I'm going to look at different types of recovery. Jane did a full simulation of this. So it's called a quasi-simulation. It's a high-level, simplified numbers underneath to illustrate it. So it's not just a picture. You actually did months of simulations behind this to look at the viability or the impact you might have if we could do what I've just illustrated, which we can't yet. We can partially do, but not fully. So we can start at the mine. We can then look at our designed upgrade where we do gang rejection, get rid of a whole lot of gang early on. And then we change our entire waste profile. We change where the waste goes to, how soon it gets pulled out the process. We then say we're processing less material, so going to use less energy. But of course, the earlier we pull out from that earlier graph I showed, the more value is sitting in the waste pile instead of in the value pile. So we've got a compromise there. And if we don't understand the variability coming through, we could be quite eagerly throwing away grade when we think it's waste. And it happens all the time right now anyway, but we could actually make it worse by implementing these. We need to have that in our understanding of the process. And then we look down, we can affect the tailings. If we're doing less fine grinding, significant impact on the tailings, the need for tailings dams. And if we don't have the fine material, our water recovery goes up, even if we have the identical flotation process. We could be floating less material, so there's less water in the process, or we could be floating coarse material, so our water recovery is enhanced. Either way, we can dramatically reduce our requirement for fresh water. So now in our study, we used a few indicators. There can be more. We just put 6 in here. The highlight things one might look at in assessing these different options we're going to try. So is it head grade and life or life of the mine? So we can improve the head grade coming to the process, but it impacts life. And we've put them in one box. So do we get enhanced head grade or do we go so far that we slash the lifetime of the mine? And therefore our effective use of the resource, which is a community asset as I see it. And then the comminution energy, pretty straightforward. Recovery, how much do we get out of what we put in? Our tailings, are we going to produce bigger or smaller tailings requirements? How much water we'll use? And without the profit, we don't even start the process. So we have to look after the profit. We can't ignore that. No mining company is going to go into business to not make a profit. Although sometimes it looks like that. But anyway, at the moment we'll say they don't wish to. So we link those to these risks. The objective is to then map it back onto the risks of any given ore body. What are the risks that preventing that one being developed? And is it going to be developed for the good of the entire society there? And now we could potentially link maybe a shorter life that makes money quickly for a big company is a bad deal for the country. They don't want that. They want that one that is developed for longer. Or maybe it is a good deal. You're in, you mine what you can, you move out, there's less impact. It depends on the environment. So we could look at all of these risks and the influence that our predictions have on those risks. We couple them. So if I start with my process of I've got an ore and a waste and a cutoff grade, my base case, I then want to look relative to that. So these are calculated numbers. Doesn't mean that they're real numbers, but they're realistic numbers, should we say. So I do a pre-concentration of the mine side, kind of to maximize the head grade that I'm processing. And so the head grade goes up, the power goes down because I'm processing less. My recovery goes down because I'm dropping my grade, my total recovery from the mine side. Okay? I'm rejecting a whole lot early on, unavoidably. But I make some more money and I definitely save on water and things. But I have reduced my resource. So this is quite common to do now, and it can be quite a winner for a mine site, for a mine. I can then look at upgrading my feed and pushing up my throughput, and my life plummets because I really just push away anything that's not favorable to process today, and I dump it to the side. So my power goes down, my recovery might be better because my grade going to the plant's a bit higher, so that recovery at the plant's better. I make some more money now, but I really have slashed the life of mine. And then I've got a staged upgrade, and we can now change our cutoff grade. So we upgrade the feed a bit further, and we can keep that upgraded feed or move it to a bigger block of our mine site. So we're changing where we do the work, where we do influence the process. And each of these have a different impact. Some reduce the life, some increase it, some are neutral, some make more money, some don't. So what we want to do is run this and maybe 30 more scenarios. But this we just did one direction. What you would want to do is loop that back around the circuit, back to the mine plan, the way you blast, the way you mine. So you want to be able to loop around. So actually to do this effectively, you need to do it iteratively, of course. And that would be the process. That's why it's in that wonderful circle that we've got. So maybe this one looks the best because I get a better overall use of my ore body. I use half the energy, half the water. I drop my tailings requirement by 40%. I make 20%, 28% more profit. They should be saying, woo-ha, I want to go there. But that process we haven't built yet. So how do we certify it'll actually do that? And that, to me, is the bit we're missing. That's the bit I'm campaigning for. Not like the other guys out there doing other campaigning. I'm campaigning for that. Actually, that's where we put our effort. It's into the basis of being able to predict these influences. And then we can look around the risks and map them. We've only done it for a few. How did it map onto these various risks? If you present that mapping of the risk back to the nation, back to the community, back to the state, isn't that the way you're going to move these complex ore bodies, these ones that are not available to being utilized, and actually find out whether they are utilizable or whether we shouldn't be at this stage until we have better technology. I might just point, until we can fix this bit in the process to make it more effective, we shouldn't exploit it, because then we're just exploiting it. When we can fix that, we're utilizing it. I deliberately don't use exploit, by the way, because then I'm just exploiting it. If I have the right technology, then there's the time to utilize it. And it can drive technology development, because you can put a what-if scenario into this modeling. So I can go, but what if I could make that process use 20% of the energy? What's it going to do? You put it in, you look at the effect all the way down the process chain and say, this is amazing. Everyone says, yeah, if you could do that, it's amazing. I say, great. What I need is $20 million, and I'll go and invent it. Great deal. I mean, a single company might go for that, because they've put billions into the place already. Say, well, if you can solve that, I'm with you. Couldn't we do that? We could get a single company to pay for a piece of technology if you can totally demonstrate the value to the process. So that kind of brings me to the conclusion. Part of it is, hopefully it's a process we can drive forward. It's a process people will be interested in. I'm more a spokesman than, I don't own it. I'm not just a spokesman. It's here to be debated to see if you think there's value in what we've put together here. This is a long thought process, not I woke up one morning and got inspired. I woke up 183 mornings and got inspired with my colleagues to put this concept together, that we can look, it all comes back to what's in that rock, what's the mineral association, underlies all of this. It's the technology to empower us all the way through the chain. Because I see our social environment colleagues, they tend to see, and society very much, we're just a fixed process. You dig a hole, you put it through a whacking great big mill, you produce X amount of tailings and X amount of waste pile, done. Now, how are we going to deal with that? And I disagree with that. I think that's totally wrong. With this process approach, we could look at totally changing how a local community, a society interacts with an ore body. How a mining company makes a really good deal out of the middle set of it, the big profitable bit, but you can make it into a community asset in the long term. And so you don't have a mine that goes and just stops, ka-chink, and then you get your community and environmental disaster. So instead of closing a mine, you wind it down really gradually and it has the assets and the people around to keep running it. That's just one dream of mine. It can be completely different scenarios. But I'm hoping this might be a pathway forward to address those. Thank you.